There are two main ways to cope with motion. The first is to prevent it. Avoid your participants from moving. How can we do that? Well, a number of ways. For example, some scanners, you see this is the coil of a scanner, have a little bite bar. So your participant is biting on this bar, and that prevents them from moving their head too much. In other cases, you can build these horrific sort of soft plastic masks that kind of really nail the head of the participant to the coil, to the bed rather of the coil. And this is sort of a similar thing. You can also use sort of these kind of apparata to sort of keep participants as still as possible. My sense is that while these all sound great, the truth is that your participant will have an itch in their nose, and they're gonna, for example, up here, they're gonna try to wiggle a little bit to sort of scratch the itch at the point of their nose, and they'll still move. And you know what? They're still gonna breathe. And the heartbeat is still going to induce movement in the brain. Every time your heart beats, the veins that climb up the brainstem will kind of tug on the brain. So my take is that typically for your average participant, just putting pillows around them and trying to sort of immobilize them by putting pillows around them and trying to constrain their head with soft pillows is usually the best strategies. You can do other things, but this, on average, works pretty well. The second way of coping with motion is after motion has happened, you want to model it. In other words, remember, it's all about signal to noise ratio. We want to maximize the signal, which is what we know, what we can explain, and minimize what we can't explain, the noise. So one way is to explain the noise, to turn motion into something we can explain. In other words, model it. This will remove it from the unexplained variance or the noise. Let me show you what I mean. Let's just assume that this is our experiment. This is a coronal view of a brain. Let's just take this voxel right here, just because it's a voxel I picked. What you're seeing here is the time series of that voxel. Let's just assume that our design was this, was baseline, task, baseline, task, baseline, task. And see here, this dip here, that's probably motion. See, this one here also is probably motion. So what you could do is when you analyze the data, this is saying, hey, software, hey, statistical analysis, this is when my task was off, and this is when my task was on. This is when it's off. So your software knows that any change that goes up and down together with your task is signal, is what we want to explain. So you can also say, hey, not only there's this task going on and off, do note that at some point there was a big motion, and it was right here. So any change in the time series that happens exactly, with this, that happened exactly at this time point, it's about motion. It's not about anything else. So take it away. This way, we're explaining this big peak right here. It's a way of explaining things and removing them from what we can't explain. Now, sometimes we do this, but more conventionally, what we do is we take those, remember the graphs I showed you from FSL? We take those exact graphs. So this red line is how much did we have to move the brain, each volume, from left to right in order to fit it into the reference volume. So for example, we didn't have to move it too much, then suddenly here we had to move it a lot, right? So here there probably was a big motion, and then not too much. And then this one is the back to front. So we had to translate it a little bit, here a little bit, and then that way. And here we had to translate it quite a bit. It's probably that motion right there, et cetera, et cetera. So we take, by how much we had to rotate or translate each volume, and we use that inside our statistical model. In other words, we're telling the statistical model, hey, not only there was my task, but the head of the participant also moved in all these points. And so, for example, see here where there's a lot of movement, both in the side to side, back to front, and also rotation in the roll direction. We're telling the software, hey, look, any change that happened at this time, it was probably motion, so remove it. Remove it from our task. Again, this is a way of removing things from unexplained and making them explained. So that when we do our signal to noise ratio, what we can explain versus what we can't explain, we're decreasing the things that we can't explain. Now, there's one important point to make with respect to motion. See, sometimes the way in which correcting for motion affects your data and your statistical analysis can differ. Let me explain. Look at the graph on the left. This is an analysis that was run, and you're seeing here some significant voxels. And this analysis was done without doing motion correction. So if you came to me and said, hey, Professor Monti, I just ran this analysis, it's kind of odd, I get these weird voxels here or there, I would say, hey, are you sure you did motion correction? And you go like, oh, no, gee, I'm so sorry, I forgot. So I'll say, okay, go away, redo the analysis, do motion correction. You come back, and now suddenly we have some nice activations. It makes sense, right? Because in the prior analysis, what you did is you had a lot of motion in the unexplained variance. So in other words, the denominator of your t-test, right, the noise, was very big because it had in it all this uncorrected motion. By doing motion correction, effectively what we did is we removed variance from the denominator of the t-test. Therefore, because we removed variance from being unexplained to being explained by motion. So now when you show me the t-test, well, now it does show significant foci that do make sense. So the typical result of doing motion correction is that you usually get activations because you were artifactually not getting them earlier because there was all this noise that you hadn't corrected for. Sometimes, however, you get the exact opposite. So sometimes it might happen that before correcting for motion, you get a ton of activations, right, everywhere. See, here, 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 here. And then you say thing, and you discover you forgot to do motion correction, so you redo the analysis with motion correction, and somehow now your activations have gone down. That's odd, right? We just said that we are doing preprocessing in order to get a better signal to noise ratio. We should get more significant voxels. Well, see, the difference is that up here, the motion was uncorrelated to your task, so it was random with respect to your task. So it makes sense that when you clean it off, it's all noise. When you clean it off, it helps your t-stats. Here, instead, motion was happening every time, was happening together with your stimulus. And so remember the big changes in values that noise, that motion can create, those giant spikes in the data? Well, the statistical model thought that all that variance was because of your task. It didn't know it was motion. So it makes sense, just imagine that your task is showing participants, normal pictures versus very scary pictures. Maybe every time they see the scary picture, your participant moves just a little bit. Right? Has this just a slight reaction correlated with your task. So now when you do scary pictures minus non-scary pictures, what you're getting, the difference between the two is not only that one is scary and one is not, but this is scary plus motion systematically versus non-scary. So there's a lot of motion that the software, that the analysis mistakenly thought was due to your task because it happened together with your task. So it makes sense that after you do motion correction, you're getting rid of that. You're saying, oh, no, this looked like it was task, but it was actually motion. And so it makes sense that after that, you would get lesser activations. So if you do an analysis with and without motion correction, and you get fewer activations after the motion correction, you have to be careful. You have to be mindful that that motion was probably correlated to your task. One thing that gives it off in a way is, see, when you see activations that follow the profile of the head, follow the profile of sort of changes in intensities, that often is motion. So you want to be careful to always decouple motion-prone events in your design with your task of interest. For example, sometimes pressing a button, might make somebody move. So you want to decouple pressing a button to respond from your stimulus of interest. Maybe you want to show a problem to a participant, and you ask them to solve it, and then you say, once you've solved it, then just wait and answer when I tell you to answer. In other words, you're decoupling the cognitive process that you want to image from anything that might induce motion, such as pressing on a key. All right. So if you're designing an experiment, if you can, try to decouple anything that can create motion with your task. You do not want motion, stimulus or task correlated motion, because it's very difficult to fix. Or rather, you risk taking away from it, you risk taking variance that is about your task away, thinking that it's motion. So if you can, always try to decouple motion-prone events in your design and the cognitive, the periods that you want to image of your task. Now, finally, there's also a way of correcting motion as it happens, and it's known as prospective motion correction. So this is an actual MRI sequence that tries to correct for motion. Let me give you an example. So let's just assume that these are volumes that we are acquiring. In fact, let's assume that we acquired a first volume, and the box represents the MRI machine, what it's imaging. And then let's assume that our participant moves a little bit. Now, prospective motion correction sequences, what they do is in between TRs, usually takes about 80 milliseconds. They take a super quick image of the brain and try to detect whether there's been motion. So they take a super quick image of the second volume, they compare it to the first, try to see if there's been any motion, and if it detects any motion, it moves the acquisition together with the motion. So it tries to estimate, did you move your head? And if it does, it kind of moves the camera with the head. And so in other words, you can imagine the MRI machine trying to follow the head as it moves. Of course, it sounds wonderful, and it does have a lot of pros. However, it's not perfect in the way that it moves. So some motion still remains. So it is very important to mitigate motion as much as possible, possibly prevent it. But if you can't, do use one of these strategies in order to mitigate it. I have to confess, however, even if you do this, it doesn't fully solve the problem. See, the reason is that a number of movement artifacts still remains. For one, if you remember the video that I showed you, it didn't clean when I showed you side by side the pre and post correction time series. It didn't fully correct for motion. Even though we had greatly reduced the motion with motion correction, there still was some motion in there. So we didn't fully correct for all the motion that is inside the time series. Furthermore, you should keep in mind that there's some types of motion that are just very difficult to detect. See, the way in which we see that motion has happened is that we take one volume and we see if there was a lot of difference with some reference volume. Imagine this. Imagine that a participant, started here, then during the TR, they suddenly did this, and then before the TR is done, they go exactly right back to where they started. It'd be impossible for you to detect that within TR motion, because we can only detect well across TR motion. So even though, there are means to mitigate motion, they're really not perfect. So the best strategy is always to try to prevent motion from happening beforehand. Now, very important, always try not to have task correlated motion, because that you can fix it, but even if you fix it, you might be stealing actual variance from the brain and incorrectly attributing it to motion. Finally, you should keep in mind that motion does not correct for spin history effects. See, you remember that protons get entrained by the radio frequency pulse. So protons get entrained into a cycle of radio frequency, down, sort of come back up, 2 seconds, and then radio frequency, down, back up. Imagine that a certain proton is inside a slice because your participant moves, and now that same proton is in a different slice that is acquired earlier in the TR. Now suddenly you do radio frequency pulse, down, and now the next radio frequency pulse, because the proton moved into a different slice, will happen before the proton will have fully relaxed, which means you're going to get less signal from that proton. So motion affects the spin history of protons, and it's perfectly possible that just because somebody moved, in the next volume, that certain proton will not be, you will not be able to stimulate it because it hadn't yet relaxed, because it was not expecting another TR. It was not expecting, excuse me, another radio frequency pulse for a while, right? So in the normal sequence, it would have still had time to relax. But because it moved, and it moved up in a sequence, that in a slice that was acquired earlier, you won't be able to effectively stimulate it. In other words, the values that you get in the next TR will be off, just because of spin history effect. And finally, you can also imagine that if the magnetic field is not as smooth, is not perfectly smooth, just by moving, now different voxels might end up in slightly different magnetic fields. And this too will introduce noise, and that we can't correct for. So what's the moral of the story for motion anyways? Well, as much as you can, stop people from moving. When you put your participant inside the MRI machine, make sure they're comfortable. If it takes an extra couple minutes to make them comfortable, it's time well spent. Because if they are uncomfortable, you better believe that over the span of an hour, they will be moving to try to make themselves more comfortable. So spend an extra few minutes to try to make your participant as comfortable as possible. Tell your participant, look, just so you know, motion is a big problem. If you can, during the data acquisition, while the machine is beeping and is on, try to move as little as you possibly can. And if you really have to scratch your nose, do it when the MRI machine is not acquiring data. And finally, something that we do often, particularly for difficult populations, children, for example, you can train participants to stay as still as possible. For children, for example, we often put them in mock scanners, and then they play a little video game inside mock scanners. But the twist is that there are little sensors attached to their head, so that anytime they move their head, the video game freezes and they can't play. So children get very good at keeping their head still with this type of training. So you could possibly, if you know you're working with a difficult population, you can train them to move as little as possible. Now, if motion has already happened, and you already have data at hand, then do your best to try to mitigate it. Correct for motion, use motion correction, and model it in your statistical model. Again, what you're trying to do is you're trying to remove unexplained variance or noise. And you know what? If one data set is just too bad, throw away the data set. I mean, reject an entire subject. If you have a subject that just moved too much, they just move too much. It's bad data. You don't need it. Throw it away. And of course, how liberal you can be with this depends on your study. If your study is a study of any average 22-year-old, and there's a large population of 22-year-olds on campus, then you're probably better off saying, this data set is just too much motion. Let's acquire one more participant. Of course, if instead your data set is this, this very rare person that you flew in from the South Pole because it's one of two people in the whole world that have a certain genetic mutation, and you can't fly them back, anytime soon for the foreseeable future, sure, then you're going to try to bend backwards and sort of jump through hoops to save the data. But short of that, if a data set is bad, it's just bad. And finally, as well as you can, try to decouple motion-prone tasks from the cognitive event of interest. So if something in your task is at risk of inducing motion, try to decouple it from the cognitive events that you want to image. As I said, if it's about responding, ask your participant to respond after the cognitive process you care about.